Imagine having the power to, completely brick the front door of your company's most important server with just a single typo.
Oh, yeah. It happens way more often than you'd think.
Right. Today, we are looking at that terrifying, almost godlike power of the Linux system administrator. Because, if you're prepping your Fedora Linux virtual machine for Dave Reed's Class 7 lab, you are about to inherit a massive responsibility.
You really are. You're managing human beings on your server.
Exactly. And human beings are messy.
Dave's course notes actually open with a line for the CS123 System Administration course that captures this, ultimate sysadmin sigh of resignation. He writes, "Users. If only systems didn't have users."
That is so true, though.
Right. A computer system sitting in a server rack, disconnected from the world, is perfectly predictable. It's just a closed logical loop that does exactly what it's programmed to do.
It's pristine, just a beautiful humming piece of logic, but then, you have to actually let humans use it.
And that's where the trouble starts.
Yeah, humans forget their passwords, they save massive files they don't need, they try to access folders they shouldn't even know exist. Suddenly that pristine logic has to build walls and set rules to handle all that human chaos.
And that tension between machine logic and human behavior is our entire mission for this deep dive. We're exploring the complete life cycle of user account administration today.
So we're going to give you the exact tools you need for your lab to construct this digital society, basically.
Exactly. How to bring a user into the system, how to manage their social interactions and boundaries, and importantly, how to safely evict them when it's time to go.
I mean, every user has to start somewhere, right? So let's create an identity. Say we hire a contractor named Ann Appleby, and we need to let her into the machine. I assume we don't just, type a generic command and hand her a blank slate.
Well, you use the userAdd command, but doing it correctly is kind of an art. By default, userAdd just carves out a tiny, unprivileged, bare-bones space on the hard drive.
Just a completely empty room.
Yeah. But a seasoned administrator builds the user's entire profile right there in the initial command line by stringing together different options.
So you aren't just creating a login, you are defining her existence on the server. You'd attach her actual human name to the account using a comment flag, the dash flag, so she isn't just floating around as the cryptic username, Appleby.
Right, and you might tack on an expiration date using the E flag, say March 31st, 2026, if you know her contract ends then.
Which is super smart, so you don't forget to remove her access later.
Exactly. And you also want to give her the tools she needs to do her job immediately. In the notes, Ann Appleby is assigned to a secondary group right away using the -G flag.
Ah, right, the wheel group. She's added to wheel from the very moment her account is created. I have to pause on that, though, because wheel sounds like something out of a medieval fantasy novel, not a corporate server room.
Yeah, it's a classic piece of Unix lore, actually. Historically, being in the wheel group meant you were a big wheel, like a person of importance.
Well, a big wheel, that makes sense.
All right. In modern Linux systems, adding someone to the wheel group gives them pseudo privileges. It allows them to execute commands as the root user, the super user.
You are essentially handing Anne the keys to the kingdom.
Pretty much.
Okay, so we've built the house, we've put her name on the mailbox, we've even given her VI key access. But she still can't actually get inside, can she?
No, because by default, password access for a brand new account is completely disabled. To let Anne in, the root user has to intervene using the password command.
So the administrator could just set a password for her, email it over, and be done with it. But the notes suggest a much more secure trick, right? Forcing an expiration immediately.
Yes, using the aexpire flag with the password command. You give her a temporary password, but you flag it to expire the very second it is used.
Oh, that's clever.
So when Anne logs in for the very first time, the system stops her dead in her tracks. It essentially says, "Welcome. Now change this password to something only you know before you take another step."
It enforces personal accountability from second one. She can't blame IT if someone guesses her password later because only she knows it.
Exactly. But the section in the notes on what that new password should actually look like completely flips the script on what most of us have been taught about security.
Oh, I loved this part. The mathematical reality of password cracking is entirely at odds with human psychology.
It really is. For decades, IT departments have forced users to create complex, painful passwords, requiring a capital letter, a number, a special character, no dictionary words.
And you end up with something totally unpronounceable, like capital JDI 74% sign, AKUAISJ %sign 6.
Right, complete gibberish. Now, according to the security analysis in the notes, it would take a computer about 15 billion years to crack that specific string of characters through brute force.
I mean, 15 billion years sounds incredibly secure.
It is?
But my human brain cannot hold on to that string of garbage. I am guaranteed to forget it by tomorrow morning, which means I'm going to write it on a sticky note and stick it under my keyboard.
Which completely defeats the billion-year math.
Exactly. Anyone walking by can just look under my keyboard.
So look at the alternative the notes provide, a passphrase instead of a password. The example given is, ketchup ruined my cereal.
Ketchup ruined my cereal, sad face. I will literally never forget that phrase for the rest of my life.
Exactly, because it paints a ridiculous, memorable picture in your mind. But mathematically, because of its sheer length, it would take a computer 200 septillion years to crack that passphrase.
200 septillion. Wait, so the silly sentence about cereal is exponentially more secure than the complex string of characters.
Exponentially.
And my human brain can actually retain it.
Yes. Length defeats complexity when it comes to brute force computing attacks. A long string of easy-to-remember words is mathematically vastly superior to a short string of random characters.
That is a perfect example of aligning security protocols with actual human behavior rather than fighting against it.
It really is.
It's like, you know, when you start a new job and the security desk hands you this heavy, convoluted lockbox for your ID badge, telling you it's the only way to be safe, and now they are finally admitting, actually, just a really long, funny lanyard works better, and you won't leave it in your car.
Yeah, it's a highly effective, human-centric approach.
Okay, so Anne has her ketchup passphrase. But what actually checks that password? When she types it in, what part of the system is analyzing her input and deciding whether she gets access or gets locked out?
Well, the command password doesn't exist in a vacuum. It relies on a foundational framework in Linux called PAM. That stands for Pluggable Authentication Module.
Okay, PAM.
Think of PAM as the central nervous system for authentication. It lives in the etc.d directory.
But why does Linux need a separate module just for authentication? Why doesn't the login screen just check the password itself?
Because hard-coding security into every individual application is a nightmare. Imagine if the local login screen, the remote SSH server, and the smart card reader all had to independently write and update their own security checks.
Oh, that sounds awful. They'd all be out of sync.
Exactly. So by making it pluggable, whenever a program needs to authenticate a user, it just asks PAM.
So PAM is the ultimate authority. It's like the bouncer checking the VIP list, looking for fake IDs, and forcing the lockouts.
Yes, and a system administrator can swap out the rules without rewriting the core operating system. You want to require multi-factor authentication. Plug that module into PAM. You want to lock an account after 3 failed attempts. Configure that in PAM.
And to configure those rules in modern Linux environments like Fedora, the notes point us to a tool called authselect.
Right. Authselect is designed to safely manage these complex core configuration files. But the notes issue a very stark warning here for anyone doing research online.
Oh yeah, this is the danger zone.
Huge danger zone. You will likely encounter older tools like authconfig and a graphical version called authconfig GTK. These are deprecated. Do not use them.
They will mess up your system.
They absolutely will. But more importantly, whether you are using the right tool or editing files manually, you must treat PAM with extreme caution.
What is the actual worst-case scenario if I make a typo in a PAM configuration file?
You can break the authentication chain so thoroughly that absolutely no one can log into the system.
No one.
Not Ann Appleby, not the other users, not even you, the root super user. You turn the server into an impenetrable vault.
Oh my God. So I've essentially installed the state-of-the-art security system on my house, but I botched the wiring on the keypad. Now I'm standing on my own front porch in the rain.
Yep.
My own house won't let me in. I have the key, I know the code, but the bouncer is brain dead and just saying no. How do you even fix that if you can't log in?
You have to break a window.
Literally.
In Linux terms, yeah. You have to physically go to the server console or the virtual machine console and force the system to boot into single user mode.
Wow.
This bypasses the normal boot process and the network entirely, dropping you into a minimal root shell for the sole purpose of fixing the text file you broke. It is a highly stressful emergency recovery situation for any system.
Note to self, do not experiment with PAM right before leaving for the weekend.
Good rule of thumb.
Okay, let's assume Anne is safely past the bouncer. She is inside the system. But a server is a collaborative space. She needs to share files with the kitchen staff without exposing them to the accounting department.
And this requires understanding how Linux organizes users into a social hierarchy. The information is split across two main files.
Right.
The etcbred passcode file holds the basic user info and their primary group. Everyone have one primary group. But users need to collaborate across multiple teams, right?
Right, you're not just in one department usually.
Exactly. Those secondary affiliations are held in a file called etc. group.
Now, the notes mention a few ways to peek into these databases. You could just search the text files using grep, but there are dedicated commands that give you a much cleaner picture.
Tools like getInt, which stands for get entries, actually query the system's databases directly. But even better is the id command.
Yeah, id is super useful.
If you run a id followed by Anne's username, it checks both files and outputs a clean list of her user ID, her primary group ID, and every single secondary group she belongs to.
Let's say we have a group called cooks, but the company restructures and wants them called chefs. I assume we just use a modify command.
You use group mod with the nenen flag. You can rename cooks to chefs without messing up the underlying group ID numbers that the computer actually uses to track permissions.
So the human-readable name changes, but the mathematical ID stays exactly the same.
Exactly.
Okay, so the chefs group is ready. To put Anne into it, we modify her user profile. But there is a massive trap here for beginners when adding someone to a secondary group.
Oh, this catches everyone. You use the usermod command, and you absolutely must use the append flag, the A, alongside the secondary group flag, G.
And if you don't?
If you just use N and G and tell the system put Anne in the chefs group, the system assumes you are providing a complete overriding list of her secondary groups.
Ah, so it sees chefs and thinks, okay, she is only in chefs now.
Yes. It drops her from every other secondary group she was in.
Including the wheel group we put her in earlier, so she instantly loses her pseudo privileges.
It is a silent demotion. Always append when adding secondary groups.
That silent demotion is brutal. Okay, so Anne is safely appended to the chefs group. But the notes highlight a really quirky behavior about how Linux handles these secondary permissions. Let's say Anne wants to create a file that belongs to the chefs group. She can't just do it automatically.
No, she can't. When you log in, your active session is tied to your primary group. Even if you are a recognized member of chefs, the system doesn't apply those specific collaborative privileges to your current session automatically.
Really?
Yeah, you have to explicitly tell the system, I am acting as a chef right now, using the new grep command.
It is literally like wearing different hats.
Yeah.
Anne has her standard employee hat on. She has the chef hat in her locker. She is allowed to wear it. But she has to actively type new grep chefs to physically put the hat on her head before she starts generating files that need to be owned by the chefs group.
Right. It enforces the principle of least privilege. You shouldn't walk around with elevated departmental access active at all times. You only put on the hat and use the power when you need it for a specific task.
Okay, Anne has her chef hat on. She's collaborating. But what if she gets a little too enthusiastic? What if she uploads like 500 gigabytes of uncompressed 4K recipe videos? The server doesn't just run out of space for other people's files, does it?
Oh, a full file system on a Linux server is catastrophic.
It crashes everything.
It can cause core system processes to crash because the operating system itself has no space left to write its temporary files or the system logs. The whole machine just seizes up.
Okay, so we need boundaries. We need disk quotas to curb the hoarders.
Exactly. Quotas prevent any single user from taking down the ship. And what's vital to understand here is that quotas aren't just some software layer running in the background. They're baked into how the hard drive itself is mounted to the operating system.
And that starts in the etc. stab file, right? The file system table.
Yes. That file tells the computer how to attach the hard drives when it boots. To enable quotas on traditional X file systems, the admin edits that file to add the usr quota or grep quota options to the specific drive's configuration and then remounts the drive.
Once the drive is tracking quotas, how do we actually define the limit for Anne? The notes talk about setting limits on blocks and inodes. I understand blocks, I think. That's just the physical size of the data, right?
Yeah, think of a block as roughly 1 kilobyte of physical space. Limiting blocks limits how many gigabytes of data a user can store. Inodes, however, are entirely different.
How so?
An inode represents the existence of a single file, regardless of its size.
Wait, so if Anne creates a million tiny one-sentence text files, she could exhaust the system's inode capacity even if she's only used a few megabytes of physical block space.
Precisely. The system requires limits on both physical size and total file count. For traditional file systems, you use the edquota command.
And that opens a text editor right in your terminal to set these numbers.
Right. And for both blocks and inodes, you define a soft limit and a hard limit.
Let's use the notes example for Anne. They give her a soft limit of 500,000 blocks, which is roughly 500 megabytes, and a hard limit of 550,000 blocks.
Right.
The soft limit is like getting a warning text from your credit card company. Hey, you are nearing your credit limit, but you have a grace period. The system lets you exceed 500 megabytes temporarily, so the video you are currently saving doesn't just fail and corrupt.
Exactly. You're given a window of time to clean up your files.
But the hard limit is the bartender cutting you off. Your card is simply declined. At 550 megabytes, the system just says, disk quota exceeded. You cannot write another byte.
It is an absolute physical boundary. Now, your lab environment might use modern file systems like BTRFs, and BTRFs handles data fundamentally differently than older block-based systems.
Right. It uses concepts like subvolumes.
So the underlying architecture is different. You don't use the old edquota command.
You have to use tools built specifically for that file system architecture.
Yes. You use commands like btrs quote enable and btfs group. The underlying philosophy of soft and hard limits remains the same, but the vocabulary the SysAdmin uses changes completely depending on the architecture of the hard drive.
Makes sense. Okay, we've brought Anne into the world, we've managed her groups, we've limited her storage, but eventually the contract ends and Appleby is leaving the company.
Yep.
I want to remove her from the system. The intuitive move would be to use the userdel command and just wipe her home directory at the same time to keep the server clean.
That requires adding the MAR option to the command, which tells the system to recursively delete the user's entire home directory. And the notes heavily flag this as a dangerous practice in a corporate environment.
Really? Why? It sweeps the floors, clears out the desk, she's gone.
Because Anne wasn't just working on personal vanity projects. She was likely working on collaborative scripts, departmental documents, critical data.
Oh, true.
If you aggressively delete her directory, all of that institutional knowledge is vaporized instantly.
Okay, so we run the basic remove command without deleting her directory. We delete her login, but leave the files sitting on the hard drive. But who actually owns those files now that Anne doesn't exist?
This gets to the core of how computers actually think. To the file system, files aren't owned by the English name Anne Appleby.
Right. The computer only speaks math.
Exactly. Files are owned by her numerical user ID, her UID, which might be something like a 1002. When you delete the account, the human name is erased from the registry, but the files on the hard drive are still stamped with the number 1002.
So the files are just sitting there attached to a ghost number.
We call them orphaned files, and they represent a massive security risk. Let's say a month later, you hire a new intern, you create an account for them. The system looks for the next available user ID number. It sees 1002 is vacant because Anne is gone.
Oh, no.
It assigns 1002 to the intern.
Oh, wow. So the moment the intern logs in, the file system looks at them, sees the number 1002 and says, welcome back. Here are all of Anne's highly sensitive corporate files. The intern inherits everything simply by recycling the old ID number.
It is a profound security failure.
So what is the actual secure workflow for retiring a user?
It must be a phased retirement. First, you temporarily disable Anne's account so she can't log in while you sort things out.
How do you do that?
You do this by changing her login shell to a dead end, typically banal again.
The bouncer just turns her away at the door.
Then you find the person replacing her, or her manager. You systematically reassign all of her important files to the new responsible party using the change owner and change group commands, chown and CHER.
Ah, so you hand over the keys to the physical filing cabinets before you finalize the paperwork.
Only after the files are safely reassigned and you are certain there will be no orphaned data waiting to attach to a new employee do you finally run the command to remove her account. It is deliberate, careful, and secure.
Which brings us to the ultimate application of all this knowledge. If you are a student in Dave Reed's CS123 class, listening to this deep dive to prep for your labs, it is time to face the music. Lab 7 is upon you.
You have the blueprint, you know the workflow. Now it's time to actually build and manage this mini society on your Fedora VM. And Dave is checking these VMs.
He absolutely is. The homework is due Tuesday night, March 17th, right after spring break. So let's run through the checklist. You need to create user accounts and assign them initial passwords. You need to create groups and assign users to them.
And do not forget to append when adding secondary groups.
Yes, a flag. You need to alter a primary group and test that it worked. There is an optional task to test disk quotas for the home directory. And remember, the notes specify you should research how BTFs handles this, not just traditional systems.
Right. You'll also need to practice temporarily disabling a user using that binlogin shell.
And finally, the ultimate test. Reassigning files to an alternate user and safely removing an account without leaving those dangerous orphan files behind. Then, and only then, you can enjoy your spring break.
It's a comprehensive lab that really forces you to execute every phase of the lifecycle we've discussed today.
We've mapped the entire digital life of a user. From the moment of creation, securing the front door with passphrases and PAM, organizing social hierarchies with groups, setting physical boundaries with disk quotas, and orchestrating a secure departure.
It is a massive apparatus of control.
It is. And, when you look at all these rigid defenses, the PAM lockouts, the hard disk limits, the careful management of orphaned files, it makes you wonder about the future.
How so?
Well, as artificial intelligence gets better at managing these systems dynamically, will the role of the sysadmin shift? Will we stop manually configuring these rigid mathematical rules and instead just teach an AI how to judge human behavior and enforce these boundaries in real time?
Transitioning from programming the machine to simply guiding its judgment. That's fascinating.
It's something to think about while you configure your virtual machine. Next time you get locked out for a typo, just remember, the machine is just trying to protect itself.